In the last video we looked at how a large unstable nuclei decays by emitting an alpha particle. You should be getting used to the symbols now for A, Z, X, Y, and we also introduced the alpha particle. A, the number of nucleons, Z, the number of protons, X, the chemical symbol of the initial element, Y, the chemical symbol of the new element, and the 4,2 alpha is the alpha particle, which is given off through our alpha decay. In this video today we're going to be introducing some new symbols. Have our symbol for a neutron, a proton, an electron or a beta minus particle, and an antineutrino. Now just a point of reference here, if you see a chemical symbol, if you see a symbol that has this little dashed line over the top, it means it's an antiparticle. So we obviously have neutrinos, but we also have antineutrinos. Okay, so beta minus decay occurs when a nucleus has an excess of neutrons and involves the decay of a neutron into a proton with the emission of an electron, which is a beta minus particle, and an antineutrino. And we can see that diagrammatically represented along here. It's important to note at this point that the atomic numbers or charge is conserved during the decay. So the electron charge of the neutron is equal to 0. So the complete charge on the right hand side of the equation must also equal 0. And you can see proton having a +1 charge, electron having a -1 charge, and the antineutrino having a 0 charge. Pretty simple. 1 plus -1 plus 0 gives us a net charge of 0. So the general equation for beta minus decay of an unstable nucleus is given by our initial element decays into our new element with an electron and a antineutrino given off. Okay, so in practice what this looks like is we have our carbon-14 nuclei here. The carbon-14 is going to decay. We're going to have the A stays the same. Now the number of protons, we're going to go from 6 to 6 plus 1, which is 7, which means we have a new element. And the rest of the equation is already written out for us. So we're going to be going from carbon-14 to nitrogen, plus an electron and an antineutrino are both given off in this case here. You're not going to get an equation as simple as that usually in a test. So if we're moving into a testing situation, we might get something that looks a little bit more like this one here. You might be asked to solve for strontium undergoes beta minus decay to form yttrium. Write an equation for this. So the first thing you'll be doing is writing down your symbols. Now, important to note at this point that the equation list will have the equation for beta minus decay along with all the others. It will be up to you to recognize which decay is happening and which formula to use. So that's probably the most important thing, is to be able to recognize which equation goes with which decay. But you'll get given most of the information that you need. So we're starting with our strontium, and that's going to decay into 90 Z plus 1. So 39 yttrium, and we're actually already given that, so we don't need to go look that up. And we know we're going to end up with an electron and an antineutrino. So in reality, the only thing that we actually needed to calculate in this scenario here was 38 plus 1. This is realistically the only thing we needed to calculate in that. We knew the new element being formed was going to be yttrium. We knew this 90 at the top was going to stay the same, and the 38 is going to turn into 39 protons, and we know what's going to be left over this side here. So beta minus decay, the hardest thing I think is going to be remembering which equation to use at which time, but the actual maths behind it is quite simple. Thank you.